let's actually take a simple example to analyze how do we apply the differential form of mass conservation, right? So again, let's write down the differential form of the mass conservation, the divergence of V equal to 0. Or if you wanted to write it in more recognizable form, it's partial U, partial X, plus partial V, partial Y equal to 0. And let's see how this equation works around a stagnation point of an airfoil. So what is a stagnation point? A stagnation point for an airfoil, this is, I think, let's see, how do I just draw this without my hand moving the screen itself? Okay, so this is an airfoil, and the stagnation point is a point that actually terminates on the surface, on the leading edge of the airfoil. So essentially, this is a streamline that separates the flow that goes below the airfoil from a flow that goes above the airfoil, right? So this is the stagnation point. And as you can imagine, if you happened by luck to be sitting on a particle that is on the stagnation streamline, what happens is that you are never going to reach the airfoil, right? So you have a streamline that goes towards the airfoil, but you are neither going to go above or go below the airfoil. So it looks like you're going to collide against the airfoil. But as you're going to see in a moment, the flow, as it approaches the stagnation point, which is the intersection of the streamline with the airfoil, it is going to slow down. And as a result, you're actually never going to get there. So let's look at the flow field. And let's look at the flow field essentially by zooming very, very closely into the leading edge of the airfoil. We zoom into this very tiny purple region here and magnify this purple region and rotate it so that the flow field looks like this. On the magnifying glass, the curvature of the airfoil disappears, right? Just like the Earth is round, but like if you zoom into the ground, you're going to see the Earth is flat. So this is pretty much happening to the airfoil too. If you zoom very, very into the leading edge of the airfoil, the curvature kind of is negligible, and you're going to see the airfoil, the leading edge of the airfoil, pretty much like a flat wall. As you approach the airfoil, what is the flow field? What does the flow field look like? Okay, so here we should now be looking for a solution to this mass conservation equation and figure out what should the flow field look like very, very close to the airfoil. Well, it turns out in this case, we do have an analytical solution to the mass and later on momentum conservation equations. Let me first write out the solution for you. So in this case, my U, so let's actually take a coordinate system. So let's say the stagnation point is the origin, and X direction points into the airfoil, and the Y direction points upward. And the X and Y coordinate also determines what I mean by U and V, right? U is the X component of the velocity, and the V is the Y component. So if you take a streamline here, this is the vector V, and the X component is U, and the Y component is V. Okay, so the solution here is U is equal to a proportionality constant times minus X, so minus lambda times X, and V is going to be the same proportionality constant times Y. Okay, so let's first of all check that the solution makes sense physically by looking at the streamline here. Okay, what we are seeing here is essentially the X velocity is proportional to the magnitude, is proportional to how far away we are from the wall. So the further away from the wall, right, it means the x component of the velocity is going to be larger, right? So this point has a velocity vector like this. So the x component is going to be more because it's away from the wall. And if you're closer to the wall, the velocity is like that, and the x component is correspondingly smaller. So that's what it means physically. Also, the y component follows a similar trend. So if you are above the stagnation streamline, the y velocity is positive, and if you are below the stagnation streamline, the y velocity, so this is u, the y velocity is going to be negative, right? And also, the further away you are away from the stagnation streamline, the larger the y velocity is. Basically, the further away, the faster you are moving away from the stagnation streamline. So this is what this solution tells us physically or intuitively. But what's important is to check this against the mass conservation equation, or the differential form of the mass conservation equation. So in this case, we're going to see partial u partial x is what? If you take the derivative of minus lambda times x, the derivative is minus lambda, right, everywhere. Similarly, if you take the derivative of v with respect to y, the derivative is plus lambda. So if you add them up, well, if you add them up, you get 0, right? So basically, this equation is correct. Okay, so this is one of the simplest solution of what we are going to see, the Navier-Stokes equation that describes the that fully describes the mass conservation, momentum conservation, and energy conservation, right? So this is one of the simplest solutions, and the manifestation of mass conservation appears very simple from the proportionality of u and v. And here you can see that only this solution works, right? So if you, for example, if you take u equal to not the negative, but the positive lambda times x, it will not satisfy the mass conservation equation, right? We're going to have two positive lambdas. They don't add together to 0. All right. So